In this unit, we are going to be talking about chemical equilibrium. And equilibrium is actually not a new term for us. We've actually looked at it in two previous units. We looked at it in the gas unit when we were talking about evaporation. When the rate at which molecules leave the liquid form to become gases equals the rate at which gases then reform to become liquids, you have reached a state of dynamic equilibrium, meaning the two rates of the opposing processes are equal. We also looked at it when we were in the solution unit, specifically when you have a high concentration of solute that has been dissolved, you will reach the point at which your solution is now saturated, meaning if you add any more solute, no more will dissolve. And the reason why was because if you have enough solute that has dissolved into its ions, then that increases the probability that those ions will strike the solid and crystallize. So at that point, the rate at which ions are being formed by dissolving equals the rate at which solids are reformed by crystallization. Those are two opposite processes. So when the rate of them are equal, you are in a state of dynamic equilibrium. So in this unit, we're going to be looking at equilibrium, but specifically for chemical reactions. So we call that chemical equilibrium. So again, chemical equilibrium occurs when opposing reactions are proceeding at equal rates. Now, the important thing for you to know specifically for chemical reactions is it's when the rate at which the products are formed from the reactants, so that's the forward reaction, equals the rate at which the reactants are formed from the products. So that would be the opposite process, that would be the reverse reaction. So those two are equal. When they are equal, you are in chemical equilibrium. So there are two requirements for equilibrium to occur. The first one is that the concentrations of the reactants and the products can no longer change with time. The important thing to keep in mind is the fact that the reaction is still occurring, you just don't see any change in concentration. That's why we call it dynamic equilibrium. The second is that neither the reactants nor the products can escape from the system. If those two conditions are met, you're in equilibrium. So if you look here at these two graphs, at A, what this is showing you is that at time equals 0, you have N2O4, but you have no NO2. So what that tells me is that N2O4 can either be my reactant or my product. And what this graph is showing me is that even though I don't start off with any NO2, I will eventually reach equilibrium. And after that dotted line, what you should notice, since your y-axis is concentration, yeah, they're not equal. Your concentrations don't have to be equal to be in equilibrium, but notice they are not changing concentration. So after equilibrium has been reached, the concentration of NO2 and N2O4 do not change. For B, what this is showing, notice that the rate at which N2O4 disappears and NO2 forms after equilibrium has been achieved, those rates are equal. Here what this is showing you, these two graphs show you that it doesn't matter whether or not you start with your reactants or your products, you can still reach equilibrium. So the graph on the left-hand side shows you that you start with your reactants, H2 and N2, and NH3 is your product. So you start with just your reactants, but you're still able to reach equilibrium because the concentration of NH3 increases until you reach equilibrium. Notice it's equilibrium because the concentration of those three substances do not change. For the second graph on the right-hand side, notice I start with what I would consider typically my product, and I start with no reactant, and yet I still reach that same equilibrium. So it doesn't matter what you start with, as long as you provide your reaction with the conditions, a closed system, necessary for equilibrium to be established, equilibrium will be established. So now that we've talked about chemical equilibrium qualitatively, let's talk about it quantitatively. So what I have right here is just a generic reaction. Keep in mind that the lowercase letters represent your coefficients while your uppercase letters represent your substances. And I have this double arrow. Notice it's a half arrow on top and then on bottom. You can't just draw a double arrow. And that represents the fact that that reaction reaches chemical equilibrium. So the law of mass action actually expresses the relationship between the concentrations of reactants and of the products once you have reached equilibrium. So specifically, the equilibrium constant expression, that demonstrates the relationship as expressed by the law of mass action. So specifically what you do is you say the constant, your equilibrium constant, which is your Kc, that equals the concentration of your product, D, raised to its coefficient times the concentration of E raised to its coefficient divided by, and then the same thing but this time with the reactants. So notice your products are in the numerator while your reactants are in the denominator. And we actually get this equilibrium constant expression by noting the fact that the forward reaction equals the rate of the reverse reaction and actually using your rate law. Okay, so you can actually see how that is possible if you want. Do notice that the rate law that I'm using to create this equilibrium constant relies on stoichiometry and not the laboratory techniques that we used before. So what this table is showing you is a bunch of different experiments in which I start with different concentrations of N2O4 and NO2. N2O4 is my reactant and NO2 is my product. So notice for experiment 1, I start with no N2O4 but a little bit of NO2. The next one still no N2O4 but a little bit more of NO2. And you can see how all of these are very different. What you should notice though, yes, the concentrations that they reach when they're in equilibrium are different, but look at their equilibrium constants. They're all the same. And so what this demonstrates to you is that no matter how much reactant or how much product you start with, once these reactions reach equilibrium, and you can actually calculate their equilibrium constant, at the same temperature, the equilibrium constant will stay the same. If you change temperature, then the equilibrium constant will change, but otherwise it will stay constant. Up until this point, we've been talking about the equilibrium constant and the equilibrium constant expression in terms of concentration. Well, we can actually also write this in terms of pressure when we're dealing with gases. And so this is actually how we would write the equilibrium constant expression for pressure. It's your Kp. Kp is your equilibrium constant now. And now you just use partial pressures rather than concentrations. So this is extremely similar to the equilibrium constant expression for concentration. Now, how do we relate our equilibrium constant for concentration to that of pressure? Well, if you remember the ideal gas law, if we change this around just a little bit by dividing both sides by V, you get that pressure equals your number of moles divided by volume times RT. What you should recognize is the fact that N over V, that equals concentration. Okay, so that represents PA is the partial pressure of A equals the concentration of A times R times T. And so all you have to do now is substitute in your Kp and your Kc. The only difference being the other thing you have to consider is delta N. Delta N is the change in number of moles of gas. So for example, if I start with 1 mole of gas on my reactant side and I end up with 2 moles of gas on my product side, then my delta N would simply be 1. If I end up with the same number of moles of gas on both sides, then my delta N would be 0, and my Kp would actually be equal to my Kc. So it's the only thing that you have to additionally consider. But here's this right here is the equation for relating Kp to Kc.